Okay. Let's just practice taking antiderivatives a little bit before we move on. Start off with a polynomial. Oops, wait a second. Sorry about that. There we go. Do let's do those. That's just a little practice. The first one is just a polynomial. We're going to use the antiderivative power rule on that. And on that, at least the x squared part on that. And we know how to take the antiderivative of a constant. So antiderivative of x cubed, the n here is 3, so 1 over 3 plus 1, 1/4, plus antiderivative of x squared would be 1 over 2 plus 1, 1/3 x cubed. So 1/3 x cubed times 10 is 10/3 x cubed. Remember, above the x, we have an invisible 1. So the antiderivative of x, the 1, is 1 over 1 plus 1, 1/2 x squared. But the whole thing's multiplied by 3, 3/2 x squared. And the antiderivative of 1, antiderivative of 1 is just x. The antiderivative of 5 would be 5x. And don't forget to put in your plus c. Oops, hang on. I see I forgot I wrote 1/4 here, but I forgot to write my x to the 4th. There we go. There we go. Now I think we got it. 1/4 x to the 4th plus 10/3 x cubed plus 3/2 x squared plus x plus a constant. And again, if I ever make a mistake like that again, leaving something out or putting something in that's just crazy, please feel free to tell me. I won't be offended in the least. Okay, so secant squared, we know that the derivative of tangent is secant squared, so the antiderivative of secant squared is tangent. And we have to be a little careful with this We look at that and we say, that's not a power function. That's an exponential function. The variable is upstairs in the exponent. So we're going to use the antiderivative rule for exponentiation for exponent functions. And so what we have here is, when we take the derivative of 2 to the x, we have the original function 2 to the x, and we multiply the whole thing by natural log of 2. Going backwards, we just divide the whole thing by natural log of 2. In other words, multiply by 1 over the natural log of 2. Taking the derivative, we would multiply by natural log of 2. Taking the antiderivative, we would divide by natural log of 2. First thing we notice is this is an exponential function, not a power function. And don't forget to put in your plus c. So something like this, there's no antiderivative product rule, but that's okay. We can just do a little bit of algebra here. Algebra is our friend. X times x is x squared. X times minus 5 is minus 5x plus 3x, so that's minus 2x altogether. 3 times negative 5 is negative 15. Notice that the integral sign and the dx are still there because I haven't done any calculus. I've just done a little bit of algebra. And now we can go ahead. We have a polynomial, same as we had in the very first example, an easier one in this case. I can go ahead and take the antiderivative of each of these terms. Antiderivative of x squared is going to be 1/3 x cubed minus antiderivative of 2x. Antiderivative of x would be 1/2 x squared times 2, so the 1/2 and the 2 cancel out. That's just x squared. Antiderivative of minus 15 is going to be minus 15x, and we'll put in our plus constant. So the moral of the story for C and a couple of those questions we did last time is that algebra is very much your friend. And if it looks like you don't have any techniques to do the problem with what you know about calculus, try a little bit of algebra first and see if you can massage this thing inside here is called an integrand. See if you can massage the integrand into a form where you can apply the rules that you know. Okay, so let's move on to section 4.2. Which is called area. I want to start off with a classic problem. So remember, in a circle, radius r, picture here. So r is just the distance between the middle of the circle, of course, and the outside. That's what a radius is. That the circumference is equal to 2 pi r. 2 times pi times the radius. Where you know pi is that irrational number, a little bit bigger than 3, 3.14, and so on. Say we just knew this. We knew that the circumference was 2 times pi times r. And our goal is to find a formula for the area of the circle. in terms of radius. Now, if I were sitting in your shoes, I'd be saying to myself, well, I already know a formula for the area of a circle in terms of radius. I know you do. I know you know that the area of a circle is pi r squared. But unless I'm very much mistaken, you were just sort of told that. Somebody just said the area of a circle is pi r squared. Here, memorize this, and that's that. What I'd like to do, when I say, I want to emphasize this word find, I want to start with the knowledge that the circumference is 2 pi r and work out for ourselves that the area of the circle must be pi times r times itself, pi r squared. So just based on this knowledge, I'd like to work out the formula for the area of a circle. Does everybody understand the difference between, what you've done before probably, which is just being told that the area of a circle is pi r squared and sort of working it out for ourselves, just starting with this? Is that making sense? Cool. Okay, so let's see if we can reason this out for ourselves. What I want to do is sort of think of the circle as a pizza. I'm going to redraw that circle. And I would like to cut that pizza into 8 slices. So 8 equal size slices. You can tell my picture's a little wonky. Hopefully yours is better. And I would like to lay these pizza slices out like so. So I'm going to take this slice right here, whatever, they're all the same. And let's see, it's about that big. I'm going to lay it right here. Point down. So that's, if that's slice 1, that'll be slice 1. And then I'll go to the slice right next to it and lay it point up. So if this first piece was crust up, this second piece is going to be crust down. This was a slice of pizza. I'm going to do the same with the other 6 slices. So 3rd slice, 4th slice, 5th slice, 6th slice, 7th slice, 8th slice. And of course, the shape I end up with down here has no name. That's not a shape we have a name for. It has kind of a bumpy top and these slanty sides and a bumpy bottom. But it looks a little like a parallelogram. Yeah. So this distance from here to here, that slanty distance, from there down to there, sort of measured along the edge, that's just one of these radii. Each one of these cuts is the length of a radius. So that's just the length of r. And you can see this sort of bumpy distance, there to there to there to there. This distance. Following the, following the bumps, following the pizza crust. Since half the pizza crust is down here and half the pizza crust is up here, that's just half the circumference. So this is 1/2 of the circumference. half of it's down here, half of it's up here. So this is 1/2 the circumference. And since the circumference is 2 pi r, that's 1/2 of 2 pi r, which is just pi times r. So like I said, this shape has no name at all. But you can see that this slanty distance is r. And you can see that this sort of bumpy distance is 1/2 of the circumference, because half the crust of the pizza is on the bottom and half the crust of the pizza is on top. So at least we can see that. Is everybody following me so far? Awesome. Now what I'd like to do is exactly the same thing. I want to start with our pizza again. That is a sad looking pizza. Let me try again. That's really bad. Still looks more like a potato, but we'll just work with it. This time, and it still has radius r. So same pizza, same size pizza anyway. But this time, instead of cutting it up into 8 slices, I want to cut it up into a lot of slices, like let's say 1,000 slices. So there we go, there we go. There's 8, and then 16, and then we'll just keep going and going until we have lots and lots of slices, like 1,000 equal slices. I don't know. You get the idea. So cut it up into a lot of slices. And then we're going to lay those slices up the same way we laid these slices out. So the first one with its point down, and the one next to it with its point up, and the one next to it with its point down. This is going to take all day, so I'm just going to go. These are supposed to be just slightly bumpy lines on top and a slightly bumpy line on bottom. I don't know if you can even see that in the picture. So we have a similar looking picture here, except these bumps are not so pronounced. They're very tiny now. And one thing that should be obvious, this distance r is now almost straight up and down. Not quite, but very close. And this distance all the way across the bottom, that sort of slightly bumpy distance, this is still 1/2 of the circumference. In other words, just pi times r. And this shape here is starting to resemble a rectangle. The more slices we cut it into, the closer it resembles a rectangle. If I cut into 1,000,000 slices, your eye couldn't even see the difference between that shape and a rectangle. It would look very rectangular. You wouldn't be able to see the fact that the top was bumpy and the bottom was bumpy, and you wouldn't be able to detect the difference that this wasn't quite straight up and down. If I cut it into 10,000,000 slices, it'd be even closer. 100,000,000 slices, it'd be even closer. This is starting to look like a rectangle, and the area of a rectangle is length times width. The length of this rectangle is pi r, and the width of this rectangle is r. Pi times r times r. Pi r squared. So we were able to start with this as our beginning knowledge, that the circumference is always 2 pi, a number a little bit bigger than 6, times the length of the radius. So the length of the circumference, if I want to walk all the way around the circle, that length is going to be 2 times pi, 6.2 something, times as long as it would be to walk from the edge of the circle to the center, or the center to the edge. That was our beginning knowledge. And from that, we were able to deduce that the formula for the area of a circle, which you already knew going into this, but you'd just been told, different to work it out yourself, that the formula for the area of the circle is pi r squared. And our technique was to take the area and slice it up sort of cleverly into finer and finer and finer bits. So this is very much a calculus idea, but this specific example with a circle was done long before calculus was invented by Newton and Leibniz. This goes all the way back to Archimedes. If you know the story about, Archimedes and the crown and running through the streets yelling Eureka, that's the guy. Okay, so let's take a look at a region whose area we haven't a formula for. So circle we already knew, we just sort of confirmed what we knew, and I wanted to illustrate the idea that we can chop up the region into smaller and smaller bits. So let me give you this problem. Estimate the area under the curve y equals x squared above the x-axis between x equals 0 and x equals 1, as follows. This is what we're going to do. So let me sketch that region first. Put one right here. Put one on the x-axis right here. And you know what y equals x squared looks like. It's just a parabola. Not bad. So I want the area, I want to estimate the area of this region here. I'm not going to shade that in because this picture is going to get too complicated if I shade it in. But this region right here, the region under the curve y equals x squared, above the x-axis, between x equals 0 and x equals 1. So this closed-in region. That's not a region that we have a name for. Not like a circle or a triangle or anything. It looks a little like a triangle. What we're going to do, and I haven't finished explaining the problem yet. So by breaking the x interval 0, 1, the region on the x-axis between x equals 0 and x equals 1 into n equals 4 equal parts So when it comes to these kinds of problems, I'm always going to use n to refer to the number of parts I want to break my interval into. So let me just go ahead and break this interval 0, 1 into 4 equal parts. If I break 0, 1 into 2 equal parts, I have to cut it at 1/2. And if I break each of those into 2 equal parts, this is at 1/4, and this is at 3/4. Again, if you are not as enamored with fractions as I am, if you prefer to do this with decimals, 0.25, 0.5, 0.75, I think it's easier to work with fractions, for me especially, but you don't have to share my taste. So we're going to break that interval 0, 1 on the x-axis into 4 equal parts, and we'll construct rectangles on each part that touch the curve on their right-hand side. So again, let me illustrate what I mean. What's your finished copy? So let me pause and wait for you to catch up.
Right before rectangles, it says construct, correct?
Yeah, it says construct.
Okay, thank you.
You have no problem. Always let me know, again, when I pass that minimum level of legibility. And I know there's an extra issue here just because of the fact that you're not in a classroom with me. Which for a variety of reasons right now may be fortuitous, since this office is so full of chalk dust right now, you have no idea. So probably better for your respiratory health that you're not in here. So the first rectangle is going to touch the curve. Let me just sketch this a little bit. I think that's closer to what the curve actually looks like. So the first rectangle is going to be between x equals 0 and x equals 1/4. It's going to have its base along the x-axis, and it's going to touch the curve on the right-hand side, so at 1/4. The right-hand side of this interval from 0 to 1/4 is at 1/4. So it's going to be right here. That short little rectangle which touches the curve right there. That next rectangle is going to go between 1/4 and 1/2, and it's going to touch the curve at its right-hand side. In other words, at 1/2. 4 rectangles. I've drawn 2 so far. The third one's going to go between 1/2 and 3/4. And touch the curve at its right-hand side. In other words, at x equals 3/4. And the last one is going to go between 3/4 and 1, and it's going to touch the curve on its right-hand side. In other words, at x equals 1. So why rectangles? Because we know how to compute the area of rectangles, length times width. We replace a problem we don't know how to do with another problem we do know how to do. So let's compute the area of these 4 rectangles all together, the area of this, the area of that, the area of that, the area of that. So let's see, we're going to construct rectangles on each part which touch the curve on the right-hand side and compute the total area of those 4 rectangles. So this is called a right-hand sum. And we have n equals 4 equal parts. So a right-hand sum with n equals 4 equal parts. Each of these rectangles has the same width, but clearly they have different heights. Okay, let's compute the heights of each of these 4 rectangles. Once we have the heights, we already know their width. Each one is width 1/4, 1/4, 1/4, 1/4, 1/4. So let's compute their heights. That first rectangle is just as high as the curve is at x equals 1/4. So the coordinate of this point, its x coordinate is 1/4. How do you get the y coordinate for this curve? If there's a point on the curve and you know its x coordinate, how do you get the y coordinate?
Square x.
Yeah, you just square it, because this curve is y equals x squared. So its y coordinate is going to be 1/4 all squared. So in other words, this point is 1/4, 1/16. 1/4 squared to square a fraction, you just square the top and square the bottom. Multiplying fractions, way easier than adding or subtracting fractions. This second point right here, which we'll need the y coordinate to tell the height of this rectangle, its x coordinate is 1/2. Its y coordinate is going to be 1/2 squared, which is 1/4. So you get the quarter by that, that's just 1/2 squared. Take the x coordinate, square it. Let me just look on the screen to see if that's visible. Yeah, okay. This third point, its x coordinate is 3/4. Its y coordinate is going to be 3/4 squared. So to square 3/4, you square the top, square the bottom, put one over the other. And this last point, its x coordinate is 1, its y coordinate is going to be 1 squared, which is also 1. So the right-hand sum is going to be the area of those 4 rectangles. So right-hand sum, we're going to abbreviate RHS, right-hand sum. So the area of that first rectangle, its width from here to here is 1/4. And its height, we said, is 1/16. So this is the area of rectangle 1. Plus, we want the area of rectangle 2. Its width is still 1/4. All these rectangles have width 1/4. So the common mistake that people will say that the second rectangle has width 1/2. It doesn't. It starts at 1/4 and goes to 1/2. So its width is still 1/4. And its height is the y coordinate of that point right there. So that's 1/4. So its height is 1/4. So here's the area of rectangle 1. Here's the area of rectangle 2. That third rectangle is again 1/4 unit wide. And the height is the coordinate, is the y coordinate of that point right there, 9/16. And this last one, its width is still 1/4. All these rectangles have the same width. And its height is the coordinate, the y coordinate of this point right there, and that's 1. Is everybody okay with how we came up with this sum? That's the area of rectangle 1, this is the area of rectangle 2, that's the area of the rectangle 3, rectangle 4, and each of those is length times width, or width times length. We good? Cool. Any more? Great. Terrific. Okay, good. Yeah, good. It always, again, stop me if there's something that's not making sense. Feel free. If there's something that's not making sense to you, I guarantee you're not the only one, but hopefully this is making sense because each of those is just the area of a rectangle, and you've known for so long that the area of a rectangle is just length times width. Okay, let's just do a little bit of arithmetic here. I'm going to do it in fractions. If you don't like fractions, please don't worry. Just do it in decimals. Pull out your calculator. That is totally fine. But 1/4 times 1/16 is 1 times 1 over 4 times 16 is 64. 1/4 times 1/4 is 1/16. 1/4 times 9/16 is 9/64. And 1/4 times 1 is 1/4. To add those up, I have to get a common denominator, which is going to be 64. 1/64 plus 4/64 plus 9/64 plus 16/64. And if you add those all up, 1 plus 4 is 5, plus 9 is 14, plus 16 is 30. 30 over 64, or 15 over 32. And if you don't like fractions, don't torture yourself. Just do it with a calculator. Okay, so the total area of these 4 rectangles is 15 over 32, a little less than a half. It's a little bit less than a half. 16 over 32 would be exactly a half. We're going to use that as an estimate of the area that we actually really wanted, the area underneath the curve above the x-axis between x equals 0 and x equals 1. So can you tell me, is this an overestimate or an underestimate of the true area under the curve? And why? How do you know? Just looking at the picture. Is it an overestimate of the true area under the curve or an underestimate?
An overestimate?
It's clearly an overestimate. And how did you know that?
Because the rectangles go over the curve.
Because the rectangles stick above the curve. That is perfect. So it's an overestimate The rectangles stick above the curve. So we know that the area under the curve is at most 15 over 32, whatever that value is. And again, this thing is called a right-hand sum because the rectangles touch the curve on their right-hand side. If we were to construct 4 rectangles with n equals 4, which touch the curve on their left-hand side, then unsurprisingly, that's called a left-hand sum. Let's just do that now quickly. So let me just recopy this picture briefly over here. Y equals x squared. It takes you a little bit longer probably to recopy my picture than it does for me to copy it. So let me just slow down for a second. Let you copy that. So what I want to do is do a left-hand sum with n equals 4. The left-hand sum, LHS. Right-hand sum, RHS. Okay. Let's break the intervals 0, 1 up into 4 equal parts. Same dividing lines as before. We cut it in half and cut each of these into half, so that's 1/4 and 3/4. So we will again have 4 rectangles. The widths will be 1/4 for each rectangle. So I'm still using n equals 4. Okay, so the first rectangle touches the curve at its left-hand side. The left-hand side is right on top of the origin. So that first rectangle is this stupid rectangle right here with no height at all. It's flat because it touches the curve at 0, 0. We can argue forever if we want, does that even qualify as a rectangle? The second rectangle touches the curve at 1/4, at x equals 1/4. Well, we already know the y value at that point. We worked it out before. So 1/4, 1/16. The third rectangle touches the curve at 1/2. So 1/2. And we know the y value for that also. It's 1/4. And the fourth rectangle touches the curve at 3/4. So in other words, at 3/4, 9/16. The y coordinate is going to be 9/16. So 4 rectangles. These 4 rectangles look a lot like these. You can see there's one clear difference. So first rectangle with the 1/4, height 0. Second rectangle with the 1/4, they all have with the 1/4, height 1/16. Third rectangle with the 1/4, height 1/4. Fourth rectangle with the 1/4, height 9/16. And a little bit of arithmetic with fractions. You could do in decimals if you like. If you like fractions, that's great. It's just a matter of taste. So we have basically 0 plus 1/64 plus 1/16 plus 9/64. Getting a common denominator and getting rid of that 0. 1/64 plus 4/64 plus 9/64. One plus 4 is 5, plus 9 is 14 over 64. 7/30 seconds. Decibels are just fine. And is this an overestimate or an underestimate of the true area under the curve?
Underestimate,
Right, it's an underestimate. How did you know that?
because it's literally like under the line.
There you go. That is perfectly clear. So this is an underestimate. The rectangles are below the curve. So we know the true area is definitely bigger than 7/30 seconds and definitely smaller than, I cleverly erased it, I think it was 15/30 seconds. Is it clear in your head that, I mean, this choice n equals 4, that was completely arbitrary. If I'd cut it up into 10 parts and done right-hand sums and left-hand sums, is it clear in your head that the upper rectangles would stick up less than it did for n equals 4, and the lower triangles would, be a better underestimate? I mean, that they would, the two rectangle sizes would be closer together if I did n equals 10, and for n equals 100, they'd be even closer together. So the upside is if I increase n, I get better and better upper and lower estimates. They're getting closer and closer together. The downside should be obvious to you right away. More work. To get the upper and lower bounds closer and closer together, I have to do more and more work. Is that clear in your head?
Yep.
Well, if you understand all that, then you understand everything I wanted to tell you today. Have a great weekend. I will see you all on Monday.
Thank you. Have a good weekend.
Have a good weekend.
Thank you.